All right, in this lesson, let's go ahead and talk about the problem of naive data preparation. The manner in which data preparation techniques are applied to the data matters. A common approach is to first apply one or more transforms to the entire data set. Then a data set is split into train test sets or k-fold cross-validation in order to fit or evaluate the model. So the steps look like number 1, prepare the data set, number 2, split the data, and number 3, evaluate the model. Although this is a common approach, it's dangerously incorrect in most cases. The problem with applying data preparation techniques before splitting the data for model evaluation is that it can lead to data leakage, and in turn, will likely result in an incorrect estimate of the model's performance on the problem. Data leakage refers to the problem where the information about the holdout dataset, such as the test or validation dataset, is made available to the model in the training dataset. This leakage is often small and subtle, but it can have marked effect on the performance of the model. You get data leakage by applying data preparation techniques to the entire dataset. This is not a direct type of data leakage, where we would train the model on the test dataset. Instead, it's an indirect type of data leakage, where some knowledge of the test dataset, captured in summary statistics, is available to the model during training. Because of this can make it a little harder to spot this kind of data leakage. For example, consider the case where we want to normalize data. The scale of the input variables is arranged from 0 to 1. When we go ahead and normalize the input variables, the first thing we need to do is first calculate the minimum and maximum values for each variable, using values to scale the variables. The dataset is then split into training and testing sets, but the examples in the training dataset know something about the data in the test dataset. They've been scaled by global minimum and maximum values, so they know more about the global distribution of the variable than they should. We get this type of leakage with almost all data preparation techniques. For example, standardization estimates the mean and the standard deviation values from the domain in order to scale the variables. Even models that immute missing values using a model where summary statistics will draw on the full dataset to fill in those values for the training dataset. This solution is straightforward. Data preparation must be fit on the training dataset only. That is, any coefficients or models prepared for data preparation process must only be on the rows that the training dataset is used for. Once fit, the data preparation algorithms or models can then be applied to the training dataset. All right, so let's high-level this now. Number 1, we split the data. Number 2, we fit data preparation on the training dataset. Number 3, we apply data preparation to the train and testing datasets, and then we evaluate the models. More generally, the entire modeling pipeline must be prepared only using the training dataset to avoid data leakage. This might include data transforms, but also other techniques such as feature selection, dimensionality reduction, feature engineering, and more. This does mean that so-called model evaluation should really be called modeling pipeline evaluation. All right, now that we're familiar with how to apply data preparation to avoid data leakage, let's look at some worked examples.